Sure. Yeah. So we are delighted to have Professor Garud Ayyankar, who is a Tang Family Professor of OR at IOR Columbia University and the Senior Vice Dean for Research and Academic Programs at Columbia's College of Engineering. He received his bachelor's in electrical engineering from IIT Kanpur and a PhD from Stanford University some years back. And his research is focused on understanding uncertain systems and exploiting available information using data-driven control and optimization algorithms. He and his students have explored a large variety of applications in many diverse fields such as ML, systemic risk, asset management, OM, sports analytics, biology. He was recognized as an Informs Fellow in 2018 and has been awarded the NSF Career Award. So
thank you, Swati.
Thank you so much, Garud, for visiting us and talking about it.
Thank you. Thank you for the invitation. It's always a pleasure to come to Georgia Tech and be dazzled by all the buildings that you guys have. In contrast, Columbia seems like this scrunched up place, or as my colleagues, because I now wear this research dean hat, says, we are forced to be friendly because we can't get out of each other's ways. So anyway, it's a pleasure to be back after a fairly long time. All right, I'm going to be talking about work that I've done jointly with my PhD student, Madhu Shridharan. She's a third-year PhD student now. And as I was mentioning before, this is my foray into causal inference using techniques that I know, which is optimization. So it's a question, I wanted to get into causal inference. I wanted to understand what are the interesting problems there. And this optimization route was a way for me to get in. The next, down, okay, up and down is a little bit. So I'm going to show you a cartoon of causation versus correlation, because this is a slide that's sort of there for those of you who do not know the issues around causal inference, and there may be PhD students who don't fully know what's causal inference. So I'll start from a simple example, and then I'll delve into what I'm more interested in. Okay, so consider this graph. This has been stolen shamelessly from some place on the internet, I don't even remember. And pretend that you are running a clinic and patients are coming into the clinic and you are asking them how much exercise did you do the past week, and you're measuring their cholesterol level. And let's say over time, each dot here is a different patient. You plot it, and that's the graph that you end up getting. The correlation here seems to suggest that if you exercise, it's bad for you. Your cholesterol is going to go up. And that's clearly not something right. There's something missing here, something's happened. And what has happened is that we threw away a confounder or a latent variable or whatever else that you want to call it, which connects to both of these variables, exercise and cholesterol, and that was age. So if you take that data and then now split it by age, 10, 20, 30, 40, 50, these are all different age groups, maybe not the right representative numbers, but it's progressing age. So what's happening is that age impacts the level of exercise that you do. Age also impacts the cholesterol level that you have. If you forget about the confounder age, it looks like the relationship has flipped. More exercise gives you higher cholesterol, although in every age group, more exercise reduces cholesterol. So not knowing the confounder ends up causing a fair bit of problem. The exercise decreases cholesterol controlling for age, but if you remove this control, it has a problem. So confounders are very important. In this particular case, we also happen to be in a very fortunate situation of knowing exactly what the confounder was. And once you control for the confounder, life is good. But in many situations, they may be unknown. And this talk is about trying to understand situations where the confounders might be unknown, and what can we still do about not necessarily getting the perfect regression, that is controlling for the confounder and getting a perfect regression, but getting bounds on behaviors that we are interested in. So here's an example where a motivating example of where confounders might be absent. So let's say the question that we want to ask is, does watching Sesame Street improve reading? For those of you who have kids, this is a whatever, replace your Sesame Street by Little Einstein, replace it by whatever else is the Peppa Pig or whatever is the relevant video that your kid is watching. Now, here, there's a non-compliance problem. You're pretending that you're doing an exercise, you're going to randomly assign some people to watching Sesame Street, some people to not watch Sesame Street, and you don't get compliance. It cannot be enforced 100%. And so you have an issue, which you have a situation of this sort. Treatment was assigned, which was Z, which is 0 or 1. You put the patient either into the group of getting to watch Sesame Street or not watch Sesame Street. X is what the treatment that actually was received by the patient. They watched it or did not watch it. And Y was the observed response. Their reading went up or did not go up. And the problem here is that because it can't be enforced, there may be latent factors that impact both the treatment received and the outcome received. So a kid might be inherently interested in reading for whatever sets of reasons. That person also inherently wants to watch Sesame Street. So if whether or not you'd put them into the Sesame Street category, they would have watched it anyway. So the outcome is a problem, because what you want to decide is you want to answer that question. Does watching Sesame Street improve reading? And you want to kind of control for that latent feature, U, but in this case, we don't know what those latent features are. In the previous example question,
X observed.
X is observed. X is observed. I go even further in a moment. I'll just give you I'm going to observe the joint distribution of X and Y given Z. So different patients, you tell a patient, go and watch Sesame Street. Some of them do watch it, some of them don't watch it. You tell a patient, don't watch Sesame Street, and some of them still go ahead and watch it. So I'm going to assume that the data that is available to me is the joint distribution of X, Y given Z. And what I really I'm interested in answering is that question. But if somebody does X equals 1, watches Sesame Street, what happens to their outcome? And this is not identifiable because of the presence of that unknown confounder. And as a result, what I'm going to do is try to compute bounds. So for the moment, the big question that we want to think to ourselves is, how do I model this U? I have no idea in terms of how to model U. It could be a very high dimensional object. I don't even know what's the right dimension to be thinking about. Should the unknown confounder, is it continuous? Is it discrete going to happen? But what I do know is that the variables Z, Y all take binary values. In fact, binary is not, because they take a discrete set of values, whatever we're going to be talking about applies. Binary, it becomes so that these variables are binary to be able to model what is going to happen to you. Yes.
So X, Y, and Z are all observed.
Yeah.
What is not identifiable?
So the joint distribution is observed, X and Y given Z. But what I don't know is that if I force somebody to set X is equal to 1, what will be the conditional distribution of Y? So the problem is, because even if I put Z is equal to 1, because of the presence of U, the conditional distribution of X is equal to 1 doesn't tell me what happens to Y. The confounding comes from the fact that I can't force X is equal to 1 in my observations. The only thing I can do is put the patient into a particular category. There might be their own inclinations that is going to define for them whether they choose X's to be equal to 1. And therefore,
there is my probability that Y given X is 1.
Yes, but there's a slightly different, this notation of do basically says that if I force you to do it, what's going to happen? When I observe this confounds in it the fact that you have an inclination to have X is equal to 1 already because of the presence of U. If I knew the U random variable completely, I could marginalize it potentially, but I don't know the distribution of U. So for example, just to go back to the picture that I had before, this one. So I'm in this setting, on the left-hand side setting right now. I'm observing some joint distribution between X and Y. and I get a correlation which is positive, let's say. But if I had a stratification of the patients, of people, pretend U for the moment is some variable that is the intensity of liking to read, let's say. And if that was the case, by categorizing or stratifying it, I can end up getting a better relationship than if I average over it because I don't observe it altogether. Does that make things clearer?
So my argument is just, isn't this always the case? Whenever you have randomness,
yep,
it means that there are some unobserved variables.
Yep.
Hidden variables.
Yep.
That's always.
Absolutely. But so what we're trying to argue, so in which case you're in my camp, in the sense that no matter what you do, you're always going to have these unknown variables. However, if you are okay with computing something, if you're okay not intervening in the system, life is all right. So there are two things here. So one story is that you've got this system with unknown parameters. I only am interested in X and Y, that's all I care about. And the only thing that I'm going to do is look at Z. So in that situation, the data can completely answer the situation. Now what I want to do is not do that. I want to be able to go and cut something. Effectively, what I want to do is make predictions when this arrow is gone. So here's the system. This U random variable is unobserved. Every unit that is coming through the system has this arrow sitting there, meaning that they have their private copy of this random variable U. I'm sorry, I'm going to disappear from the video, but I'll come back. But instead, what I want to do is I want to cut this guy off. And when I do this probability of Y given do X, what I'm saying is, tell me what will happen if this arrow is gone. U still impacts Y, but this arrow is gone. So using observations for a system where that dependence exists, can you predict to some extent what's going to be happening in a system where that arrow has been forcibly removed? Does that sort of answer the question? All right, that's the setting. And in some cases, there are variables you can define which are able to do this problem. Here, we will not be able to exactly solve it, but we're going to try to give you bounds on it. All right. Okay, here's a more complicated problem that I'm going to come to if I get the time of showing you how it works. So this is a more realistic problem. I've got a system of progressions for a patient. Y is a progression of the disease. Y equal to 1 means the disease has been cured. Equal to 0 means that the disease was not cured, and unfortunately, the patient passed away. There are different treatments you could give. There are different pre-existing conditions that could be there in the patient. So C1 and C2 are pre-existing conditions. T1 through T5 are different treatments that could be given to this patient. This is the setup that is of the observed variables. Now, what we're going to assume is that the patients together have unknown confounders that are related to patients. There are unknown variables, as Anton was saying. There's always unknown variables that I've not measured. How do I get the C1 and C2, the conditions? I do some medical tests. There are only a finite number of medical tests that I can do. So there are infinite number of things that could be happening in their body. Call that all in UA. Right? Okay. Doctors could be biased too. And so the treatments are going to be impacted by the biases that the doctors have. And again, what I want to be able to show is, could I get bounds on what is going to happen to the patients if I do some set of treatments? So let's say the treatments are also binary, T1 through T5 take binary values. I want to be able to predict what is going to happen if I give a certain sequence of treatments. That's the idea that I'm after here, right? One thing that I want you to look at this, and if I end up not coming to the very end, there's a certain structure to this graph, which is going to be very important to me later on when I'm computing bounds. UA and UB are impacting variables that are sort of, other than the outcome variable Y, they are impacting only those variables. There's a bipartite graph sitting there. C1 and C2 is one side of the bipartite graph. T1 through T5 is on the other side of the bipartite graph. UA only impacts one set of nodes, and UB only impacts another set of nodes. And exploited in trying to compute bounds. So I just wanted to highlight that fact here before I go further. And what we'll be able to show is that for this one, you don't even have to solve an optimization problem. I'll give you the bounds that you can obtain for that probability in closed form. And this was a work that had, before this particular graph is taken from a previous work where people tried to get bounds using Bayesian methods. But we were able to discover that for these particular kinds of questions, you can get those bounds in closed form. You don't really have to even solve an optimization problem. All right. So let me go back to trying to question.
This example, in the previous example, you compute the treatment is independent of the U, the unobserved variable, but in this case, the treatment can be correlated with.
Yes, yes. On the treatment can be. So the important thing is that, since you brought up the question, I'll tell you, these UA doesn't impact Y directly. It mediates through C1 and C2. UB, which is the doctor-related confounders, it impacts the treatments chosen. So I can't have the situation where the treatment is independent of the doctor. I want to include the possibility that the doctor has some biases towards certain treatments. So it's a different, the model is different from the previous example, but we can handle this piece. But we cannot handle the piece where the outcome depends on the unknown confounders directly. Okay. All right. So the first couple of slides, I'm going to recap. Just trying to see where I'm supposed to be standing. Okay. I'm going to recap work that was done in 1994 by Judea Pearl and Balki. And they were looking at this particular graph, and what they wanted to figure out, again, going back to this problem, is I need to model this U somehow. I don't have a model for U. I have no idea what U is going to do. But I want to still be able to say something about limiting what is the worst case dimension that I could consider for U so that I can make some meaningful path forward, right? So for a given value of U, whatever that might be, it impacts the dependence of the variables. Remember, Z, X, and Y only takes binary values. So what does U do? U controls for any value of Z equals 0 or 1, what will happen to X, 0 or 1. Similarly, depending upon X and U, something will happen to Y. So already you should be starting to think that all I need to do is somehow model functions of these variables. And that's all I care about in terms of this U. If I can model all possible functions that you could be there between these variables, somehow I should be able to model that. So let's define functions. So let script f be the set of functions from Z to X. How many such functions exist? Z takes 0, 1 values, X takes 0, 1 values. There are 4 such functions. Right? Similarly, let script G be the set of functions that are going from X to Y. Again, X is binary, Y is binary. So there are 4 such functions that are available. And all that U is doing is for every choice of U, it picks a function from the set script F and a function from the set script G. So what am I doing right now? This presence of U is going to impact the joint distribution between Z, X, and Y. What I've said, yes.
From X to Y.
Remember, good question. In the observed data, what is happening is Z is being selected. You're being told, go look at Sesame Street. You might decide not to look at Sesame Street. So X is actually a function of Z, a random function of Z. What I have done is I've converted it into a deterministic function of Z and then said to you, all right, you will pick randomly a function, right? So as far as U is concerned, all I've done is I've taken these random functions, converted them to the entire gamut of deterministic functions that might exist. And all U is now going to do is pick a function from the first set, pick a function from the second set, and its method, it's done. That's all we're going to do. So now if I'm trying to model this U guy, which I have no idea, all I have to do is put probability effectively over the script F and script G. And I'm done. This will give me the right way to model the problem. Remember that bipartite graph that I talked about a few minutes ago? And for those of you who are thinking this forward, I take this graph and make it complicated. This size of these script f and script g is going to blow up. So I need to control that blow up somehow, and I want to be able to, and it turns out that on bipartite graphs, you can control that blow up in a reasonable way. All right, so let's go further. I went a little too further all the way. So what's the cardinality of the script f? I very quickly told you it's a number of input variables. So for x, there are two input variables, z and u. They both can answer the number of input variables to the power of 2. Why 2? Because x takes binary values. Similarly, more generally, it's going to be 2 to the parent of x times 2. Okay. All right. So let's label them by the elements of index the elements of script f and script g by two indices, rx and ry. They both takes values in 1 through 4, so they've got 16 of them. And the problem is that the size of this set R, the index set, is exponential in the number of arcs. So if you don't do something intelligent, you will run into trouble. Okay. One possible solution is that you could maybe aggregate things over it. Remember in the beginning of the talk, I said that my foray into this causal inference was from the optimization end of it. This is something that I've done before. Looked at a linear program and said not all variables are important. Anyway, I haven't told you what linear program I want to solve, but basically that was the trick. So this state of affairs up to this point existed in 1994. They said, okay, let's model it using these and let's see what happens. So let me go and tell you what the linear program that we want to solve and how we can potentially think about making it easier to solve. So I need a distribution over U. Hopefully I've convinced you that the only thing I care about now is a distribution over that index set R. In this particular case, it's a 2-index set. One of the indexes script F, another one indexes script G. Pretend that you are a larger graph, you'll have an index for every node in the graph. Number of functions that are possible at every node. So this set is huge. This is a very high dimensional problem in terms of variables, okay? So Z and the choice of the index set completely determine X and Y. I have basically said, you give me the index, you give me the input, I tell you what X and Y is. You tell me, and here's what the exact definition is. X is FRXZ, meaning the index value Rx determines it. Y is GRY of Y, which is basically GRY of FRX of Z. So you give me Z, Rx, and Ry, I know everything. And what data do I have? I have the joint distribution. I can write the joint distribution as a linear function of the distribution over indices. It is a linear function, as I was responding to Anton before. It is a integral over U. I don't know what U is, but I've hopefully convinced you that those indices are sufficient. I don't really need anything more. And therefore, it's simply a summation over the probability mass functions of those indices. Okay. What about my query? I'm interested in the query. What happens if I put X is equal to 1? Now that I have said that I have the whole deterministic machinery available to me, I can even write that query as a linear function of what I wanted to do, which is in terms of these indices. So that's a linear program for a lower bound. If I want to compute a lower bound for this probability, I just minimize the objective function with respect to whatever is the constraints that I had on the observations. And I could maximize it. I could give you bounds together with it. Now, if I get to the end of the talk, which I hope I will, I'll tell you how you can potentially refine these bounds. What kind of measurements would you want to do to refine it? But for now, the measurements are static. The data is already given, and I want to be able to find what is the tightest possible bound that I can give you with the data that is available. The tricky part here is the number of variables grows exponentially with the number of edges. So how does one deal with it? But the constraints and the objective aggregates over many R. So it's not as if these various index values are appearing in separate constraints. Many of them are coming up together. And is there a way that one can potentially utilize this fact to be able to write this linear program in a more concise fashion? Can I get rid of most of these variables and get you the same bound? So what we're going to do is I'm going to leverage the fact here for a moment that if you look at this representation, this representation, it's as if I've taken a function of z to x and y. And what we will discover, which the thing that we're going to leverage, is even though Rx and Ry are labeling functions very differently, their impact on x and y, the pair, many such functions will give me the same output. And if many of these functions give me the same output, there is no point for me to keep track of these functions separate. As far as the linear program is concerned, I'm only figuring out what is going to happen from z to x and y. And if that pair, somehow I can keep track of how to collapse all of those indices together, I can make a much more efficient linear program. And the question is, can we do that? So this is basically a more fancy name. I'm going to define a hyperarc to be a function that takes z to xy. I have completely suppressed the indices for the moment. I only care about what happens from z to x and y. This set R sub h basically says, take all the indices Rx, Ry, such that they give me the same performance as far as the input and output is concerned. The input is z, the output is x and y. Again, think about that bipartite graph. I've got variables on one side, I've got the variables on the other side. The function basically says, okay, there's some complicated relationship going on in between. I only want to care about what happens from the input to the output. And if the input to output are two different indices gives me the same behavior, just collapse them. Question though, which is going to come later, is can I discover that set without listing all the functions? Because if I have to list the function and then collapse them, there's no point. So I need to somehow figure out a way to collapse it without listing the function, which is coming in a bit. So Rx, Ry, as I said, just a verbal restatement to the same two constraints. And now the linear program that I solve can be rewritten as this other linear program. So over here, I have two quantities, h, which is in green. This is the set of all hyperarcs. And the name hyperarcs come from the fact that there is a hypergraph behind this that I don't want to bring up to, but if you have questions, I'm happy to answer them. So this is the set of hyperarcs where the corresponding index set is non-empty. Okay, so that's one quantity that's going to play a role. It's over here. Only those hyperarcs matter, and QH variables now refer to these functions and not to the indices. So if two indices give me the same function, I don't care. I'm just going to label them by one index. The query now again becomes very simple. It's just trying to check whether the RH is a set of RQ. RQ is the set of indices that correspond to the query. RH is the set of indices that corresponds to the hyperarc. And if this indicator variable is 1, then it contributes, otherwise not. I don't expect you to process this in real time. So the only thing that I want you to remember is what I've done is I lifted the problem up into index space. Then I'm saying all of these indices are not needed. Let me bring it back down. The question is that first, if I have to lift it to bring it down, then I don't save anything. I need to somehow figure out how to go from the lower dimensional space to this lower dimensional space without going. Right? So the big problem, yes, Shiva.
So Sesame Street example, can you give an example of how like two indices can give the same observations?
Hold that thought for a moment. In the next slide, I'm going to give you an example which might give you some answer to that. Yeah.
Ultimately, you would get a graph that has this bipartite structure with the confounding on one side and confounders on the other side and down.
Yes.
Everything else could be collapsible.
Correct. Weber, so pretend for the moment, that's a good question. Let me actually go back and show you. It's not bipartite in the full sense.
No, the sense of the connectivity between the confounding variables and
correct.
This
the only thing, absolutely. But Swati, one of the things that you'll have to worry about is the fact that T2, the outcome of T2 might impact T3. So it's not bipartite in that sense.
Right. And so all of, I'm saying like once you reduce with all of these things, then you would get a structure that
looks very close to bipartite.
like
Yes.
UA is impacting some, UB is impacting some variables, and then there is
Yes, so the rest part is the one, the tricky part. What do we do with the rest? You have to figure out. But yeah, that's the idea that we are going towards. Absolutely. Okay, where were we now? Where did I? This is all done. All right. And I'll come back to this question about that particular example in a moment. All right. Okay. So we want to efficiently characterize non-empty hyperarcs, meaning I need to figure out how to say that this set H is actually non-empty. So here's a simple example. So suppose I give you that function H of 0, Z takes only two values, 0. H of 0 be x0, y0, H of 1 be some x1, y1. Let's create these functions, f check and g check. I don't want to call it functions. Let's say partial maps that are consistent with this hyperarc H0. So the partial check would say if H of Z should be x0 if Z is equal to 0, x1 if Z is equal to 1. GH of X, G check is missing there. There should have been a check on top of that. Says that if X is equal to x0, I want the output to be y0. If X is equal to x1, then I want the output to be y1. So if you look at the end, Shiva, now to answer your question, now you get the answer. Okay, good. So now, remember, how did I get to this situation right now? What I got to this situation is to say that I want to model U. I got these indices, which are perfect modeling of U. I want to save by going to functions. Now what I'm trying to do is I'm going to look at the function. I want to decide whether this is a legitimate function, whether this is really a function from Z to X composed with a function from X to Y, right? Without giving you a proof by saying, hey, this function belongs to the set, that function belongs to the set. I want to just look at this. So if you stare at this for a moment, the implied function f check is always a function. It tells you the values for z, what will happen to a 0, what will happen to 1, it's always a function. What about g check? The check is missing, but that's what it should have been. But what about the g check function? Is it always a function? If I arbitrarily give you that map, which is always a function, H0, x0, y0, h1, x1, y1, I can arbitrarily pick whatever I want for x0 and y0 and x1 and y1. I get a legitimate function. But can it be, is it a legitimate composition? What do I need to make sure that the composition is legitimate?
Should be consistent. The Z should be same for both of us.
So Z, I don't care because Z has disappeared.
Oh, sorry, X.
Exactly, the middle guys. So all I need, there was a comment from the other side too. Did somebody comment it? No. So the only way things can fail is the following. X0 is not equal to x1. X0 is equal to x1. Happens to be a function where x0 is equal to x1, but y0 is not equal to y1. That's the only way this function can fail. Otherwise, it's fine. So the point that I want you to take away is that you just gave me these values. Here's a function that you've arbitrarily defined, and I can tell you that this is a legitimate function. The only thing you have to check is that if x0 happens to be x1, then y0 happens to be, must be equal to y1. Otherwise, it doesn't matter. It's a legitimate function. So RH is not equal to 0. This is a legitimate function. The only thing that I want to check, if x0 is equal to x1, then it must be the case that y0 must equal y1. Otherwise, you can choose it whichever way. So the important thing I want you to take away from this slide, which is what we're going to generalize in the rest of the paper, is, okay, here, I did not refer to the indices at all. I simply looked at the function and said, great, I can check this. Question is, can we generalize this to larger graphs? What can be done? This was a baby graph. And I wanted to make sure that in the baby graph, you know what's going on. But now let's try to extend it. And it was called partition graph, but for those of us in OR, we'll call it bipartite graph. Is actually, at the end of the talk, I'm going to talk about more than bipartite, and we don't know how to do that. This was introduced by Sachs in 2000. Yes, question 2020. Yes.
So you mentioned how, like, with those functions, you lifted it into a large space, and now you're collapsing it.
Yeah.
Why do this? Why could you not define the causal problem directly in terms of this hyperarcs?
Good question. You could. The structural properties of that going up and down ends up being very useful to me. So let me go back. So knowing that the program that I'm trying to solve is this one. So this program, I would not have been able to write directly if I didn't know what this set RH is. For that set RH, I have to have these indices. So after the fact, you're right, there was no need for it. But in order to now tell you how to, so I've done half the job, or not fully, but I've told you how to characterize the sets H. I haven't told you how to characterize this guy, this objective function, which is a problem. And without that indices structure, I can't characterize what their objective function looks like. But I'll get to it. Okay. So this was a partition graph. I should remember the other authors, but Sachs was the lead author. This is what I advise to PhD students: insist that you're the lead author. Otherwise, old people like me will forget your name. Unfortunately or fortunately, OR has this alphabetical. No, no. Oh, cool. Yeah. At Columbia, we usually go alphabetical. Rare cases, we go student first. But maybe it's a good idea to go student first. With people with limited memory, it's a problem. Okay, anyhow. So what these guys did was basically introduced a set of axioms that extends this idea of instrumental variables to a little bit broader setting. So they partitioned the variables into two sets, A and B. And VB, the B variables, topologically follow the A variables. So VA have a common set of confounders. VB have a common set of confounders. VA and VB, any pair does not share a confounder. So here's the example. VA is the set Z. It has its confounder set is empty because I can directly control it. This was a question that was asked before. VB is the set X and Y, and they share a common confounder U that is not confounding with Z. Okay. Here's the bigger example. Here, VA is the set C1 and C2. It has a common confounder UA. The other ones are T1 through T5 and Y, and it has a common confounder UB. They don't share a set of confounders. Right? This is an important restriction that we're going to be putting on this graph, and it helps do things. Okay, so suppose you have that setting. And now let's say that we extend the same story that we had before. Now I want to look at how can I control this. I want to translate the story that I had from before into this more general setting. So there I had these functions f and g. Now I'm going to have a big function f, capital F, which takes two inputs. The value for the input variable VA. In the simple example, it was Z. The index R. And it outputs all the variables in VB. In the simple example, the VB were X and Y. You give me Z, you give me index, I'll tell you exactly what happens to X and Y. Here, what I'm saying is you give me the VA variables, you give me R, which is the index set, and I will exactly tell you what's going to happen. Remember, this is a high dimensional problem. I never want to do this. Conceptually, I can do it, and it makes life easier. And we want to compute these same kind of bounds. For a treatment effect, if I do something on some set of intervention variables, I want to see what is going to happen to the output, assuming that I have the joint distributions as the variables. Right? This is the story that I want to get at. Again, the same story. It's a hyperarc. I write the function. Here, I'm very glibly going forward. It's not that much harder to write basically the same linear program we'll go through. It's the question now is the story of what happens with the H's and the VAs. So first, let's start with H, and then we'll go to the other one. This is, I have about 10 minutes left. Swati?
You have like 15 minutes.
Okay, good. So the first one, what I'm going to say is, it's a theorem which is basically the extension of that simple example that I had for H. What it says is that if you have a list of input and output functions, let me actually show you the code over here. So let's say that you have a list that corresponds to that function h. For all input variables, A1 through AVA, I'm telling you what the output variables are, beta 1 through beta VB. Focus one particular output, the jth output for the moment. That jth output gets impacted by only its parents. Let's say it's got only 2 parents. So it only gets impacted by the parents, other things I don't really care about. So when can I say that that function h is legitimate? That is, I can decompose it into functions that respect the graph structure. Extending from the idea from before, only thing I require is that if 2 rows on this side are the same, that is, the parent values are the same for 2 rows, the values on this side should be the same. Otherwise, it's inconsistent, the function cannot exist. So this theorem here, up there, which is written more cryptically, essentially tells you this fact. That you don't need to go to the index set, you don't need to know what the capital F function is. You just give me this table, and I can check this table and tell you whether this is legitimate or not. Okay. All right. So we no need to defer to the index. And this ends up saving quite a bit. So before I go further with telling you how to set up that LP, let me tell you very quickly on the kind of saving. So first, let's look at the index set for response function variables, meaning this is the index set that I needed. The next one, I'm just basically going from the index set to the number of functions that connect VA to VB. Already, you will see a decrease. And then next I'm saying is that of the all possible functions that can go from VA to VB, not all of them are consistent with the graph structure. So throw them out as well. And that in every stage is going to reduce the size of the LP. Here's just some, in the paper, we give you exactly how these examples A, B, C, D, E were generated. If you just look at the index set, so Balke and Pearl in 1994, this is the state of the art. This is the LP that they have to solve in order to get bounds. So I want you to focus on basically problems like example D, which has 10 to the power 57 variables, or E, which has got 10 to the power 32. So at this point, even today, we can't solve it. The middle one, already we are sort of starting to get our technology in place where we are saying that you don't have to care end to end. You don't have to care about these indices. Only thing you care about is input-output functions. Even if you did that, you end up getting a significant reduction over what was known before. Okay, and on these 1 million variable LPs, you can solve it. You can put them into a column generation technique and potentially solve it. The next one is when you start saying, okay, not all functions that sit in this set are actually valid, meaning that you should ignore them. Now you can start getting even better improvements, like this example A, it drops from 10 to the power 6 to 10 to the power 3. In some cases, we will show you, you don't even have to solve the LP. If you sit here, you have to solve the LP. If you sit here, we can show you that you don't even have to solve the LP. You can write the solution up in closed form. This gap from this place to that, from this column to that column is not uniform. It doesn't uniformly reduce. So this one went from 10 to the power 6 to 10 to the power 3. This one only went from 10 to the power 7 to 10 to the power 6. And that depends on the complexity of the graph. More nodes in the graph, more things can't be consistent, and you get reductions. If you've got a very sparse graph, then the reduction is not that much because you end up getting everything is valid. Okay. That's just a statement that it's... Now what I want to do is I want to figure out how to do the objective. How do I fix the objective? And this is the tricky part. So going back to Shiva's question, why do I need the indices? I need the indices because the objective is this, to check whether RH is a subset of RQ. And H is a function, Q is a query. I need indices for that. And this is going to be a little hairy. So let me see how much I can motivate it. So let I sub C be the variables that are critical in the intervention. There is a directed path from V to a variable VO in G sub I. Meaning what happens is, for those of you who know causal inference, the way to do this do operation is to remove certain edges. If you're doing a variable, all the inputs are killed, and you just keep the outgoing edges. So G sub I refers to a graph where all these variables I have been removed. And there is a directed path from any variable in I sub c to the output variable. So if you look at that, then the theorem says the following. This subset, this particular variable VB, VA belongs to the query if and only if certain variable values are held. So Q and Q, these come from the query. If and only if it turns out that certain subset of the VA variables and the VB variables satisfy what has been imposed in the query. Details are unimportant. If I have time at the end, I will tell you a little bit more about it. The important thing that you want to remember from this slide is the fact that there's a lot of mechanism goes behind it, but the fact that I want to check this inclusion, I can just look at some components of the vectors that are directly available. I don't have to go looking at the indices. Right? For example, these are some examples. I can check whether this set belongs to the query if and only if xn is equal to y is equal to 1. So a very simple thing that can be done. Now, there's a proof which I'm going to skip. Here's the final answer that if I want to check whether the function, the indices corresponding to the function belongs to the query, all I have to create for you is one certificate. There exists some variable v such that it satisfies the function and the corresponding set of that variable belongs to RQ. It's a very simple certificate to check. Here are some examples, there's a proof which I will not go into it. The final thing that two things that I want you to tell you more about. So let me stop here for a moment and tell you what happened in the process. The entire story is we looked at a graph whose confounders, we didn't know which dimension they lived in. We're able to bring it down to indices, and now we're able to basically show that the linear program can be brought down further by looking at simple functions. The next step that we wanted to do was look at conditions under which you end up getting that the graph can be computed in closed form. And let me end up getting a final story, which I'm going to tell you here. Here's the theorem that you end up getting, that suppose a query satisfies two things. The A set is entirely involved in the intervention, and all the variables are critical. IC is equal to I. All the variables are critical, then you can compute these things as closed form. The intuition basically is you write the LP and then you show that the LP's value can be broken up into two pieces that never overlap. And there's some algebra to be done. It's not a terribly large one. And that is the result that we use to show that this particular graph that existed in the literature, for which people were suggesting different ways of optimizing it, you can compute the whole thing in closed form. How much time? 5 minutes? Okay, tell me.
A question.
Yep.
Or we can take it off the top.
Okay. Give me 5 minutes. I want to talk about one more thing and then we'll leave it at that. So the next thing we wanted to do was we're motivated by this picture. And right now, the theory that we have developed is to say, okay, you tell me what has happened to the past patients. You've got a whole set of patients that have gone through various treatments. You know what the outcomes are. You don't know what their unknown confounders are, but everything was observed. You have this data, and now a new patient shows up. And you want to be able to figure out what is the right set of treatments to give this patient, and what is the expected bound on this variable y. What is the probability that they will be cured, right? But when you think about the setting, what's also happening is that outcomes for this particular patient, T1's outcome is known. After that, perhaps you did T2, its outcome is known. You know whether it was 1 or 0. Can you update now what will be the bound on y, given that you only have T3, T4, T5 to work with? Can you change the bounds now? So what's the difference here? The difference is that these unknown confounders that we are freezing them now. We're saying whatever was the unknown confounder of the patient, its value is it's drawn from a distribution, but it's a sample now. That poor guy is going to be subjected by a doctor who has his own set of biases, also picked by a sample and now fixed. So what's going to happen in the process is that sample is fixed. So you need a conditional way of propagating these bounds. And the question is, can we do something interesting with that? So suppose in this particular case, for the simple example, we observe something and we want to compute bounds on the query after observed it. So we have a conditional distribution that we want to worry about, because now we already have partial information about what that unknown confounder was. So the revised objective, the constraints remain the same because you're putting distributions on the unknown confounder. They remain the same, but the objective has now changed. And you can still write the objective in this fractional form now. For those of you who know linear programming, you should immediately start saying, okay, now I have a fractional linear program to work with. And why is it a good fractional linear program? Because the denominator is a sum of a probability mass function. It'll never switch signs. When you have a fractional linear program where the objective can switch signs, now you've got a problem. If you got a fractional linear program that will never switch sign, life is easy. It's just a lifted linear program. And that's what we end up showing. And in the interest of time, I'm just not going to go too much into the details of what happened over here, but pretty much the same technology works. A little bit more details, but it's not that's the paper. And the two things that I do want to talk about is one thing that we are stuck with, which is, I think, going to be interesting, is we now know how to do when the confounders are partitioned into two sets, UA and UB. You could potentially think about, again, going back to the doctor appointment thing, there are some treatments that are done by the surgeon, another set of treatments that are done by somebody in the medicine department. They potentially have their own separate set of biases. They're not correlated. Can we extend this to a finite number of sets, UA, UB, UC, partitioned set? But now the problem is that you end up getting these have a name. The machine learning community has figured out that these graphs are important. They're called quasi-Markovian graphs. Now you have a polynomial objective over linear constraints, but that polynomial is very nice. It's a non-negative sum of products. It's not a general polynomial. It's a non-negative sum of products. But we still don't know, other than the usual SDP stuff, we don't know how to do anything better. The only thing we know is you can convert it into an SDP, which is large, but these graphs are huge, and so the SDP is going to die. We have an algorithm which uses a Frank-Wolf type step, but can't prove too many things about it. And the other thing that we really don't know much about is what happens if these variables take continuous values. Of course, you can discretize it, but as those of you who are doing simulation and stuff know that if you discretize a continuous variable, there's a curse of dimensionality. Can we work with something in the continuous space? We've started to do some work on restricting it to exponential family distributions, but don't have much there. So I'll stop here. Thank you very much. Yeah.
So how good are the bounds that you get from this analysis? Like, are they in applications that people care about? Like, are they like 5% of confidence or?
So that's a good question, Swati. I mean, the thing is, unlike, let's say, approximation algorithm, right, where you know that there exists a particular bound. And if you had the optimal algorithm, you would have closed that gap, right? Here, the right question is, given the information that you have, given the joint distribution, this is the best you can do.
Right.
Now, in some cases, those bounds are good. In some cases, those bounds are bad. So the right question to ask in that setting is, what other measurement can I do? What is the right measurement to do to try to reduce these bounds? And that's a question that's a hard question to answer, but that's a direction in which we're trying to go. And one step in that direction was to look at this natural measurements that happen. So take the case of, in many settings, the places where the bounds become really bad are these Markovian settings with multiple stages. There are things happening over stages, but they're not Markovian in the sense, not just the entire history matters to you. But as you're going down this path, you're collecting more and more information about this particular unit. So you should be able to make better decisions about this particular unit as you go along. So that's our baby steps over towards answering this question. If the bounds are wide, you should ask the question, what other measurement can I make? If you cannot make any other measurement, then you're done. There's nothing to prove.
The perspective that if my bounds are too bad,
Yeah.
then probably I don't have the right model to begin with. I have the wrong model of the world in some sense.
Yes. So in that case, what I would say is that even the observed variables. So I would respond to that question in two ways. One is to say that's probably the case, but the error is not coming from the confounders. They're coming from the relationship that you're postulating among the observed variables. And that is potentially an easier problem to solve. Because you could postulate other relationships, see which one ends up getting you better. That's one thing. The second thing you could say is that the measurements that you have taken of the observed variables are probably not sufficient. In many cases, for example, I have in the theory, what I've said is basically the entire joint distribution. The entire joint distribution is measured. Typically, people don't. What they do is they take pairwise distribution. So there you can start saying, okay, let's go triples. I have more information. Potentially, that is going to reduce the gap in the bound. And that has been done in the literature somewhat. So those will be the two responses I would make to that. Yep.
Sorry, this is a very naive question. We've been talking about lower bounds.
Mhm.
Can you get upper bounds?
Yes, yes. You just,
Same-
same story. You basically, I think there was a line somewhere in the graph, which I did not, slides, which I did not emphasize. Just take that min and make it a max. And the same technology works. They're almost mirror images. The theorems are almost mirror images of each other.
I have a more philosophical question.
Yeah.
So to put the Sesame Street example, so you said how, like I asked some kids to watch and some kids not to watch.
Mhm.
And then there's confounders which actually affect whether they watch or not.
Mhm.
But then now the question we're trying to answer is, suppose we somehow force each kid to watch,
Mhm.
then how does this?
Yeah.
Why is that question interesting in the sense that how are you going to force them in real way?
Good question. Let's put it this way. The answer to that question would be, I would start at kindergarten, where there'll be a bunch of TVs, which shows nothing but Sesame Street, or I'll give you blocks. Sooner or later, the kids are going to get bored of the blocks and go to Sesame Street. So that would be my way of forcing the kid, sorry guys, you just have the block or the Sesame Street. If the answer is Sesame Street doesn't help, then I will not even bother with this. By the way, there's a very interesting, speaking of forced, there's a very interesting study that was done in Finland, nothing to do with Sesame Street. So somebody came up with this idea that you take kids who cannot read or write and make them watch TV, where it's self-captioned. So it was Finnish TV and it was captioned in Finnish. What they noticed was without any teacher saying, and the teachers were not told anything, they were just said, just let them watch TV. In some other kindergarten, they were watching TV without the captioning. And in another one, they were watching with captioning. And by the time they were into going to grade school, which they go a little later, they go at 7 years in Finland instead of 6 years, the ones which watched with self knew how to read. They had correlated. And after that, some Indian guy read it and decided to do the self-captioning in Gujarat in villages. Nothing, no other teaching was done. And adults who were illiterate started reading newspapers based on just doing the correlation. So it's nothing to do with my causal inference story, but it's an interesting, since I was thinking about how to solve your problem, this TV problem came in mind. Question.
Go back to the original central cholesterol in
Hmm?
the essence. So if I know about age, then I can put that in my regression and I can do.
Correct.
So how would this apply?
You wouldn't do this.
Okay, but if I don't know about age.
Yes.
Right? If I just get the original.
Yes. Yes. Then you would postulate their relationship between them. But the reason I can't go back to that example is I don't know how to deal with continuous variables yet. So I would probably discretize it. Yeah, discretize it, and then you can apply this theory.
And here I would be positing that there is a hidden variable that discrete something that
Yeah.
influences the relationship.
Between that influences both exercising, and cholesterol level. So if I put, so the right question to ask in that sense, I didn't do it correctly, would be that I would ask patients, to put it back into the Sesame Street example, you come in, I'll tell you, you should exercise 30 minutes every day, right? And I'll give you a tracker that's going to track whether you're going to exercise. Let's say discretized. Because of some confounding variable, you may or may not be motivated to exercise as much as somebody else who was given to the same condition. And now I'm going to, 2 weeks later, a month later, I'm going to re-evaluate what happened to your cholesterol. And then I would like to try to understand that if I had somehow put you into a equivalent kindergarten situation, saying that you need to show up in my office every day, and the only thing you have to entertain yourself is this treadmill, which is showing your favored source of entertainment, would it help? I mean, this the.
So imagine we do this, and then we compute the bounds. What do we do next?
So then would be the policy recommendation. If the bounds, as Swati was asking, if the bounds are tight enough,
Then we're like good.
then we are good in the sense that I can recommend you that this is a good policy. If the bounds are very off, then I have to do one of two things. Either I have to collect more data in various considerations, or I have to then say that maybe I need to follow the patient much more closely. Instead of recommending it, and this is actually a big thing that's related, but not exactly related to your question. One of the big things that's happening in randomized control trials right now is that they're failing at an incredible rate, and they're very expensive to run. So what these people are trying to do, which is sort of our model, like saying, if I randomly put people, what is going to happen to them? What these people are trying to do now is to follow the patients and find subpopulations where the recommendation actually worked. The issue there is how do you remove the bias on how that subpopulation was selected? So in going back to your question, I would sort of say, if the bounds are off, saying, okay, I need to make more measurements about a particular patient. There are certain kinds of patients for whom exercise is going to reduce cholesterol. For certain other kinds of patients, it's not the first line activity that we'll have to do. How to de-bias that is a tricky question.
So we should sense that there's a confounding factor that I'm not capturing. The bounds are very off.
Yes, so either that, or let's put it another way. It's not that you've captured the confounding variable, but maybe that confounding variable has a multimodal structure. So in one of the modes, one subpopulation, life is great, I'll get good bounds. Another mode, life is bad. And by looking at the patients and following them, I'm trying to basically partition the unknown confounder into spaces. Thank you.